Hi everyone, welcome to my talk. And thanks to the organizers for putting this conference together and giving me the opportunity to speak here. Today, I would like to tell you about a nice class of discrete subgroups of semi-simple Lie groups. And let me start with some examples of these objects, or even before that, with some words about what kinds of objects we are talking about. So G is going to be the special linear group, SLDR, or one of its close relatives, PSLDR or PGLDR. And the results I talk about can also be extended to more general semi-simple Lie groups, but I'm going to stick to these ones here for concreteness. X is going to be the Riemannian symmetric space associated to our group G, which we can define as the quotient of SLDR by the special orthogonal group SOD. And this is an especially nice, simply connected Riemannian manifold that's associated to our Lie group G. And there's much more we can say about this, and we'll say some of it slightly later. One thing I'll note right now is that our group G acts on X by isometries. Gamma is going to be a finitely generated discrete subgroup of G. And to avoid additional technicalities, I'm going to assume that gamma is always torsion-free. Since G acts on X by isometries, we can take a quotient of X by gamma. And since gamma is a discrete and torsion-free subgroup, this quotient is going to be a manifold whose universal cover we can identify with the simply connected Riemannian manifold X. These are the kinds of objects we are going to talk about. Let me give some concrete examples. This first example is a surface subgroup of surface group sitting inside PSL2R. PSL2R is the group of orientation-preserving isometries of the hyperbolic plane. So here, G is PSL2R, X is the hyperbolic plane, which can in fact also be described as the quotient of SL2R by SL2, and gamma is our surface group. How do we get such a surface group as a subgroup of PSL2R? Let me describe this in a little bit of detail because it will also show the connection between some of these discrete subgroups and geometric structures. So given our closed surface, say this genus 2 surface, uniformization tells us that we can put a hyperbolic metric on it, meaning a Riemannian metric of constant sectional curvature -1. And this gives us an identification of the universal cover of our surface with the hyperbolic plane. The fundamental group of our surface acts on the universal cover by deck transformations. And through this identification, these deck transformations are identified with orientation-preserving isometries of the hyperbolic plane. This gives us a map from the fundamental group of the surface into the group of orientation-preserving isometries of the hyperbolic plane. In other words, to PSL2R. This map is injective because any non-trivial element of the fundamental group gets sent to a non-trivial deck transformation. And the image is discrete because there's a minimum distance that any non-trivial deck transformation up here moves points in the universal cover. The quotient of the hyperbolic plane by this subgroup gamma, this image subgroup, is our closed hyperbolic surface that we started with. And in particular, this group is negatively curved in the sense of being delta hyperbolic. From a different point of view, the surface subgroups are also examples of uniform lattices since the quotient of the symmetric space by gamma is compact. Uniform lattices are one class of discrete subgroups of semi-simple Lie groups, which have amazing properties. But when the Lie group is of higher real rank, for example, SLDR with D being 3 or bigger, these lattices behave very, very differently from delta hyperbolic groups. And I'm not really going to talk about lattices today. Instead, I'm going to poke around and look for more negatively curved behavior in SLDR. So generalizing this first example slightly, we can take, instead of a closed surface, a compact hyperbolizable surface with boundary. Or rather, because it's cleaner to think of geodesically complete surfaces, we're going to attach hyperbolic funnels to the boundary. As in our previous example, we're going to put a hyperbolic metric on the surface and identify the universal cover with the hyperbolic plane. And then just like before, we are going to get a map of the fundamental group of our surface, which is now abstractly a free group, into PSL2R with discrete image. Such a discrete subgroup, this image subgroup, is called convex co-compact because it preserves a convex subset of the hyperbolic plane called the convex hull. Here you can see it as the universal cover of the surface minus the funnel. So it's this hyperbolic plane, but with all these half planes, which are lifts of the funnel removed. And the subgroup acts on this convex subset with compact quotient. So just the surface without the funnel. We can also show that this convex co-compactness condition is equivalent to the orbit map from the group to the hyperbolic plane. So this map being a quasi-isometric embedding for any choice of base point O in the hyperbolic plane. We can also relax the compactness assumption to allow for certain finite volume non-compact ends in the quotient of the convex hull. These ends are cusps, that is, quotients of horoballs by parabolic elements. Here, the fundamental group is still abstractly a free group, and the resulting subgroups of PSL2R are called geometrically finite. So those were some examples in PSL2R. Next, though, I'll give two examples in PSL or PGL-DR, where D is bigger than 2. So here's the slightly more geometric of the two examples. Consider real projective space of some dimension, d-1. Take an affine chart in there. So here D is equal to 3, and the screen is my affine chart. Take a convex open set omega in this affine chart, such that the boundary of omega has no non-trivial line segments or sharp points. This nice smooth curve like this. And now write odd of omega to denote the group of projective transformations which fix omega. So that's some subgroup of PGL-DR, not necessarily discrete, but we can now consider a discrete torsion-free subgroup of odd omega. And gamma is going to act properly discontinuously and freely on omega. And the quotient of omega by gamma is going to be some manifold, which we can now think of as locally having the geometry of this convex subset of real projective space. This is what's sometimes called a convex projective structure on the manifold, the quotient manifold. And these structures can be convex co-compact if gamma preserves some convex subset of omega with compact quotient. They can be geometrically finite if gamma preserves some convex subset and the quotient is basically compact, but might also have some controlled finite volume ends, and so on. Here's another example, which looks less geometric on the face of it. So start with one of our first examples in PSL2R and take its image under the irreducible representation from PSL2R into PSL-DR. This gives a discrete subgroup of PSL-DR that's abstractly a closed surface group. And we take the inclusion map, we call it rho 0, and then we perturb this in the space of representations, so the space of group homomorphisms from our abstract surface group to PSL-DR. And you can imagine these perturbations quite concretely in terms of taking a set of generators for our surface group and wiggling their images in PSL-DR. The images of these nearby representations will give us more discrete subgroups. And these representations are called Hitchin representations because of a theorem due to Hitchin from the early 90s that says the connected component of the space of representations that contains rho 0, so there's a single such component for all these rho 0, And this connected component has the topology of an open ball. So there's an open ball's worth of these perturbations that we can do. That's nice and somewhat surprising because in general, it's hard to say things about the topology of these spaces of representations. And many other spaces of representations don't seem to have such nice, simple topology. If the image subgroups we're interested in, though, we might want to know some more things about the individual representations in the component. For example, are all of the representations discrete, meaning the images are discrete, and are they all faithful? So that in some sense, we can think of these deformations as being on the level of discrete subgroups and not just of representations. In the 2008 paper, Labourie proved that yes, these representations are all discrete and faithful. In his proof, he defined and used the notion of a Nassau representations or subgroups. A Nassau subgroup is the image of a Nassau representation. And we'll come back to these. These are the subgroups which are the analogs of convex co-compact subgroups, but in SLDR or PGR or PSLDR. And the generalization of these will be our notion of geometric finiteness in SLDR. Okay, so I've sort of just hinted at one answer to the question I'm about to spell out, which is, we've talked about a bunch of examples so far. We might ask, what are some nice classes of discrete subgroups of SLDR or PSL or PGLDR, which describe features of these and other examples in a unified way? And here, nice might mean, for example, that the class of discrete subgroups is stable in the sense that small perturbations of subgroups in our class give us other subgroups in the same class. That would be useful because it would give us tools for studying these perturbed subgroups as well. Nice might mean that discrete subgroups are quasi-isometrically embedded in the symmetric space, so that the geometry of the image subgroup, which we can study using the geometry of the symmetric space, using tools from Lie theory, is causally the same as the geometry of the abstract finitely generated group. We might ask for groups to be delta hyperbolic, partly because we have lots of tools to study delta hyperbolic groups, and partly because this hyperbolicity makes it easier to establish stability. And we might also want to allow for slight weakenings of these conditions, for example, to allow for limits of delta hyperbolic subgroups, which are not quite delta hyperbolic themselves, or for instance, to allow for parabolic elements in our subgroups. And parabolic elements can in general interfere with stability or quasi-isometric embedding. So this is the question I want to give one concrete answer to today. One such nice class of discrete subgroups of SLDR that I will call relatively Nassau subgroups. In terms of some of the classes of discrete subgroups that we have seen, this is going to simultaneously generalize geometrically finite subgroups in SL2R on the one hand, and the Nassau subgroups in SLDR on the other. Okay, so in order to describe this class of discrete subgroups for you and motivate the description, let me first say a little bit more about the symmetric space. So X is the symmetric space associated to SLDR, also PGL and PSLDR. And remember, we can write it as the quotient of SLDR by SLD. This space can be equipped with a non-positively curved Riemannian metric, so that the isometry group of the space is PSLDR. I'm going to describe two particular features of these spaces: maximal flats and flag space boundaries. So X, any such X, contains lots of totally geodesically embedded Euclidean D-1 spaces, which are called for short maximal flats. Maximal because there aren't any totally geodesic Euclidean D spaces in X. Concretely, these maximal flats correspond to conjugates of the subgroup A of diagonal matrices in SLDR. And every point in the symmetric space lies in at least one of these maximal flats. And we can see this using something called the Cartan decomposition, or sometimes also known as the singular value decomposition, especially if you use matrices for computations. What does this say? It says that for any matrix G in SLDR, you can write G as the product of matrices K, A, and L in that order, where K and L are orthogonal, and A is a diagonal matrix with entries in non-increasing order. And you can see how up to applying an element of SOD on the right, this sits in some conjugate of a diagonal subgroup. Given this decomposition, we're going to call the ith entry in this diagonal matrix the ith singular value of G, and we're going to denote this by sigma sub I of G. We can compute it as the square root of the ith largest eigenvalue of G transpose G. This G transpose G is a positive definite symmetric matrix, so the square root makes sense. You can also think of the singular value more geometrically by saying you take the unit sphere in RD, you hit it with the matrix G, that will give you some ellipsoid. And the ith singular value of G is half the length of the ith longest axis of this image ellipsoid. Okay, so singular values are not eigenvalues, but they are related. So eigenvalues are asymptotic singular values in the sense that the modulus of the ith largest eigenvalue of G you can obtain as the limit of the ith singular values of larger and larger powers of G, normalized appropriately. So some examples, if you have a diagonal matrix, the singular values are the eigenvalues. If you have a diagonalizable matrix, in general, the singular values may not be equal to the eigenvalues. They also depend on how close the eigendirections are to one another. For example, one can compute that the Cartan decomposition of this 2x2 matrix, this product of these three matrices, this conjugate of the diagonal matrix, is approximately this. It's not exactly that, but these are the right asymptotics for the singular values. Notice that the singular values don't just depend on the eigenvalues, they also depend on n. The larger n is, the closer the eigendirections are to each other, and the larger the first singular value. Okay, so conjugates of the diagonal subgroup correspond to maximal flats. The locus in the diagonal subgroup, or one of its conjugates, where two consecutive singular values coincide, is special because it corresponds to where many different conjugates of A intersect, meaning geometrically where many different maximal flats intersect. And one general principle that we're going to use to navigate a little around this big, complicated symmetric space is that these intersections of maximal flats are largely responsible for the highly non-hyperbolic behavior we see in higher rank symmetric spaces, such as those associated with SLDR when D is at least 3. And avoiding these intersections in some systematic, uniform way will help us recover negatively curved behavior in the large. I'm not going to try to state that more precisely, but we will see an example of it later. Those were the maximal flats. The other thing I wanted to talk about were flag space boundaries. So suppose we have a sequence of points in the symmetric space, SLDR mod SOD, going off to infinity. We represent these points by matrices in SLDR, these matrices Gn. We take the Cartan decompositions of these matrices, and now there's a lot of information contained in this decomposition. And we're kind of going to ignore most of it and just look at the orthogonal matrices Kn on the left, or rather at the sequence of flags corresponding to these matrices. So what's a flag? Each flag is a sequence of nested vector spaces. And we get these flags by looking at where our matrix sends the span of the first standard basis vector. and then where it sends the span of the first two standard basis vectors, and so on. The space of all flags or sequence of nested vector spaces in RD is compact. You can describe it algebraically as the quotient of G by a parabolic subgroup, but I'm not going to say more about that. And so these flags correspond, they converge up the subsequence. And if we impose some additional constraints on our matrices having to do with gaps between singular values, then actually there's a well-defined limit flag, meaning there's a single limit point in the space of flags for the sequence of flags as n goes to infinity. And you can weaken these constraints slightly, and then you might have convergence not the full flag, but only of partial flags, meaning, for example, the one-dimensional spaces might converge, and the d-1 spaces converge, but maybe these intermediate dimensional spaces don't converge. In this way, we can view flag spaces as boundaries for the symmetric space, in the sense that they represent essentially different ways of going to infinity in the symmetric space. And these can be spaces of full flags, or they can be spaces of partial flags. For example, the projective space of RD, where each point represents just a one-dimensional subspace and no further terms in the flag. And here's an example. So if you take a diagonalizable matrix, and then you take Gn to be the nth power of this matrix, that sequence converges in the sense we just described to the flag given by the eigenvectors. Okay, there's a lot more, really a lot, that could be said about these symmetric spaces, but that was all I wanted to say about them here. And this is the end of the first part. In the next part, I will introduce relative hyperbolicity, and then we will put all of this together to talk about relative Leonov subgroups.